So, do you guys remember the FTC robot in 2018? 2017, 2018? The one with the catcher in the rye?
Oh,
Barely, not
the
really.
one with the glyph that has the mechanism.
Yes, yes. Yes. Do you know how they came up with the mechanism wheel design?
Well, I mean, I think I heard that mechanism wheels are good for going in directions that are not only forwards and backwards.
Mm-hmm.
So
Yeah.
then they put them sideways. And
Yep.
then it goes
Yeah,
up.
they're often called vectored intakes because they don't like a normal wheel will just suck straight back, but a vectored intake like pushes at an angle. So yeah. So actually, Darian saw 971's 2016 robot, and on the 2016 robot they had mechanism wheels, kind of like we did this year, to intake the ball, so that it would center it, right?
Yeah.
And he's like, oh, I can turn that on its side, and instead of sucking towards the center, I can suck up. Yeah. The point I'm trying to make is that taking inspiration from other places, if you understand something else, you can easily apply it to something else. So for example, we're going to understand how chain works, or how chain is made, because you can use those things in different situations. So maybe some of this stuff might be useful in some other places. So roller chain. You've seen it? Have you guys cut roller chain before?
A little bit, yeah.
Okay, sweet.
It's pretty interesting.
That's the spirit. Yeah, so we're gonna go over how roller chain's made, and then we're gonna go through how you design with roller chain. So I'll have a checklist that whenever you design with roller chain, you can use, so that make sure you don't miss anything. So, so there's two different parts to a roller chain. There's the roller link, and then there's the links that put all of the roller links together. So first we're gonna go over how they make a roller link. So the roller link has these bushings, and they're actually press fit into these link plates, roller link plates. So do you guys know what a press fit is?
I do not.
Guys, figure it out. It's in the name.
I
This
mean,
photo of Windows is going to
with
expire
this,
soon.
you just put the bushing inside the link plate in 2 holes.
Yes. So actually say that again.
For this case, you have the 2 holes on each plate, and then the bushing goes inside.
Yes. So what they do is they make it so that the size of the hole is slightly smaller than the outside diameter of the bushing. So when you push them in, like you have to apply force to push it in because there's an interference between the two. We actually use an interference fit. We press the bearings into the rollers for the climber this year? We pressed the bearings into those white plastic rollers so that they would stay in. Yeah, cool. So that's what a press fit is. Press fits generally with steel and materials like that are pretty expensive because you need to be very, very close in diameter. So the bushing outer diameter has to be really, really close to the plate hole. And it's expensive to make things that tight tolerance. So it's kind of expensive. But with the Delrin, when we did it, the Delrin actually deforms more, so we could do it relatively easily. And then, so basically, yep, so here we go. Okay, so what they do here is they take some of the link plates that we had over here, and they put some bushings on top, and then they press the bushings into the link plates, right? Okay, and then we take another link plates, put some rollers here, and then put the parts we just made on top, and then we press these bushings into the bushings that were on the part we just made into the other link plate. Does that make sense? And we make sure we don't press them too tightly together so the roller can still spin without touching the sides of the link plates. If that makes sense. Yep, so that's a roller link. Yep, roller link. Okay, now what we're going to do is we're going to put these roller links together. And so we're going to take some roller links, some pin link plates, and some pins. And basically what we're going to do is we're going to put this pin through the roller link center. Okay, and this isn't a press fit. This is a free rolling fit, right? And this pin is a press fit in these link plates. Okay, so we already made the roller links. Now what they're doing is they're putting the pins. The link plate is right below it, right? And we're going to put these pins in. And then over here, we're going to put another link plate on top, and we're going to press everything all together. So here, they're pressing the pins into the bottom link plate. They put another link plate on top, and then they press it in. And then they make sure, of course, to press at the correct distance so you don't have rubbing between the roller. Yep, great. Awesome. You got it. Cool. So we're going through all of this because press fits can be useful one day. It's interesting to know how chain is made. And it's important to know that chain is made of both a roller link and a pin link, right? The roller link is the one that's all together, and the pin link is the link that is linking all the roller links together. What this means is when you're designing a chain system, you want to have an even number of links. Because if you have, let's say you have an odd number of links. Let's say you have roller link, pin link, roller link. How are you going to attach the roller link to the roller link? You can't, right? They sell special half links to do that job, but they're much not as strong as a pin link connected to a roller link. So we do not use half links at all. If you're designing, you have to have an even number of chain links. Okay, cool. So what we're going to do is we're going to do a design calculation with this past year's robot for the climber mechanism. Okay. For the climber mechanism, I think we wanted it to be able to run about 35-ish inches. And so in order to take, we added 5 extra inches. So we want like a 40-inch run, okay, of chain. Okay. Okay. So the way that we calculate the center-to-center distance between the sprockets is we use one of these change calculators. This is also in the GrabCAD, but you can just go to the website. There's actually, you know how we pressed everything together and the roller slid inside the bushing, the pin of the pin link slid inside the bushing of the roller link, right? Remember that, how they like spin? Those spin freely. There's a little bit of slop in there, right? Because if it's exact, right, it's going to like rub on each other really hard. But if it's a little bit free fitting, there's actually a little bit of slop. So when you move the chain back and forth, there's actually a little bit of stretch in the chain. Stretch, I should say. It's just moving a little bit, right? And also, when you run a chain for a long period of time, that rubbing actually wears away at the chain, and so it becomes longer because there's more space for it to extend. So what we actually do is we add this factor right here to the center-to-center distance. So where x is the distance between the center-to-center distance in inches. So here we're going to have about a 40-inch center-to-center distance. We're going to plug it into this calculator to get an exact center-to-center distance. And then we're going to put that number in this equation to see how much we're going to add to the center-to-center distance to compensate for slack. And that gives us, this equation has worked very, very well for us, especially when we're using a 16-tooth sprocket to a 16-tooth sprocket. It's worked very, very well. And this is actually, I think the Cheesy Poofs did some experiments where they did, if the center-to-center distance is like 18 inches, how much do we want to add? Oh, if the center-to-center distance is like 30 inches, how much do we want to add? And they empirically tried everything, tried both of those things, and they came up with exact values that you should add. This is just a best fit line through the 2 points that they made. The two, yeah. Okay, great. So we're going to do this. Why is this so laggy? Okay. Okay, so here's the calculator. So usually we use number 25 chain. Do you know what the chain pitch for 25 chain is? So what the distance between each pitch, so the distance between 2 pins is. Do you know what that is? So basically, here's the chain pitch, the distance between two pins, or the distance between two pins, right? Do you know what it is? No, it's a 1/4 inch for number 25 chain. So we're going to go to our design calculator. We're going to put in a change pitch of 0.25 inches. And then we're going to use what sprockets we're using. For the elevator, we use 16-tooth sprockets. In fact, it's a little unfortunate, but that's kind of the sprocket we've standardized on. So for 25 chain, you'll usually be using a 16-tooth sprocket. It's not going on. Okay. Okay. And I'm going to just try some center distance. We wanted like 40 inches, right? I'll try like 40.125 inches. And then we'll compute. Okay, cool. So it says we need 337 links. And the length is going to be, the length of the chain is going to be 84.25 inches. Okay? Is this good? Does this look good?
Essentially,
We need to do the equation thing.
Mm-hmm. Yep. And what else is wrong here?
Well, that's
that's
odd
odd
number.
numbers.
Yeah. So that's not good. So you can't have an odd number of links. So we'll go with something else. So we'll go this, yeah. Yep. And then we add the equation. So if we go back to the presentation. Okay. If we look at this right here, see, here's a 39.875 inches. We have 335 chain links. Is that good?
That's still odd.
Yeah. So we have to do, let's do 40 inches exactly. So let's do 40 inches exactly. Okay. And then we're going to add, so yep, so this looks like it works. We have an even number of links. Great, everything looks good. 40 inches, so we're going to take our equation. We're going to take this equation. We're going to plug in 40 to here. And then it shows us that we have to add 0.053 inches. So that's very large. But in fact, that's actually what we added on the robot. And we actually thought it was going to be too loose. We were like, uh-oh, this isn't tight enough. So like, even though it's a lot, it worked out well. So, yep. Okay, moving on. The next thing that we have to worry about after we've determined the chain center-to-center distance is we have to think about, well, one, is the chain strong enough? But we'll do that a little bit later. And two, does the chain actually fit? Right? So with the climber this year, we had a really small space for the chain to fit in. Right? There's actually 3/8 of an inch between the two walls of the extrude where the chain was fitting. Right? Remember the box?
Right.
The roller box? Yeah, the chain has to fit in there. So we have to check to make sure that fits. And we also have to check to see around the sprocket. The chain, right, sticks out past the end of the teeth of the sprocket, right? So we have to check to make sure that this will fit wherever we do it. So for a drivetrain, we'd have to make sure that it fits in the tube, right? And for this, we have to make sure that we're not interfering with this plate over here. So Vex actually has this great sheet right here where it says, oh, this is hard to read here, but basically it has the type of chain that you're using. So here this is standard 25 chain. You can see this top row, right? That's usually what we use. This is number 25H, which is an alternative. So we usually use number 25 or 25H. So let's just say we're using 25 because it's 25H is actually slightly stronger and it takes up a slightly larger space. So we're going to use number 25 chain. So here it says that the outer diameter is going to be, let's see here, outer diameter is, what dimension is that? Outer diameter is 0.236 inches plus the pitch diameter of the sprocket. Okay, so we're using 16-tooth sprockets, so that's 1.273 plus 0.236, so that's about 1.5, right? inches in the outer diameter. So if we go to here, we can see that 1.5 inches is fine. We're not hitting. So that's good. Then we have to check to make sure that the width of the chain, so if we look at E here, if we look at E up here, right, it says 0.307 inches. So if you remember, we had 3/8 of an inch, right? And we actually need a little bit of wiggle room because the chain's going to wiggle on the sprocket a little bit. So this actually ends up being okay. If you're really, really tight like we were here, you actually have to think about it a little bit more and make sure everything's okay. But everything ended up being okay. If it's obviously if your space is smaller than 0.307, you're in trouble. It's not going to work. But yeah. Okay, sweet. So now we're going to talk about if the chain is strong enough. Okay, do you guys remember how much weight we spec'd the climber for?
600.
Yes, 600 pounds. So, and we used 2 chains, right? It's not even, the weight isn't evenly divided between the chains, but, so that's about like 300 pounds per chain, right? So, and how much can a number 25 chain hold?
More than 300.
Yes, 1,000 pounds.
2 on each side.
Yes, yeah, we're okay. Part of the problem was that, you want to have a factor of safety, right? And you want to be like a third, maybe a half of the total this load, so you don't unduly wear or stretch the chain. So usually, ideally, I think I'd want about 300 pounds would be my reasonable max, and we're fine with that. Yeah, go ahead.
I wanted to add too, something that we did notice is that when we only had 2 chains, it did eventually start to stretch a little bit. The tad.
We noticed that it stretched after we overloaded it.
That's true.
So they would accidentally stall it, and then
Yeah.
we would notice it was stretched, and then we'd be like, oh, you have to replace the chains.
Mm-hmm.
Yeah.
That's why this is important right there, because if you guys remember, it took a long time for us to replace the chain.
Yeah, it did. Yeah, I think the max pull of the 6 Neos was like 4,000 pounds.
Yeah.
So like, yeah.
There's a lot of power
Yes.
going on in that system.
Yes. Number 25H chain is actually basically the same dimensions as the number 25 chain. It's the plates are a little bit thicker, and it's a little bit stronger. It's 1,150 pounds. And then number 35 chain is not 0.35 inch pitch, it's 0.375 inch pitch. And it can hold 2,600 pounds. Great, cool. And then a couple things to end. You want to make sure here on this right picture, you want to make sure that your sprockets are obviously in line so that the chain isn't like in this weird thing, or maybe it's like at an angle and it's doing something weird.
Yeah, we've had issues like that in FTC.
Yes. Yeah, because of how you design it. Yes, that makes sense. Yeah, usually if you support the sprocket on both sides and you CNC it, usually you're okay, assuming that the holes are lined up. Yeah. Yep. So you want to make sure that the sprockets are in line. If not, you can get like the chain jumping off the sprocket and weird stuff. And the other thing you want to make sure is that you have, if you're driving, if a sprocket is being driven by the chain, you want at least 120 degrees of wrap. So if you look right here, see how it says 120 degrees? So you want it so the chain is going at least 120 degrees around. If you don't have at least 120 degrees, you're at more of a risk of the chain skipping. I don't know if you've ever heard chain skip before. Yeah.
It's not good.
Yeah. So if the chain is too long, like you haven't tightened it correctly, it can skip. Or if you don't have enough chain wrap, it can skip. If you look at this one right here, this only has 90 degrees of chain wrap, but this isn't being driven. This is just what we call an idler sprocket. It's just there to keep everything tight and running in this particular pattern. Yeah. Great. Awesome. So here's the general design. Use an even number of links. Calculate the center to center distance with the calculator, and then add this factor to use this equation. Make sure that the chain is strong enough. Now that you guys know about torque, you can actually do calculations like that. Other than the simple, obviously the simple case this year was we want to lift 600 pounds, so it's easy to calculate that way. But and then you want to make sure that the chain fits. And then these are just things that usually end up working out, but you just still want to make sure. You want to make sure the sprockets are in line and that there's at least 120 degrees of wrap. Yay, that's it. Yay.
Yay.
Any questions?
No? No?
Yay, homework.
Yay.
Oh, more homework.
You always give homework.
Yes.